So in this week of the lecture, we will be having this wide fraction calculation for the microfluidic flows, and at the same time something about liquid regimes in the microfluidic channel, like if two liquids are flowing. So this uh, different flow regimes that you see in this microfluidic channel is generated because of different stresses or forces which are there and which are becoming the factor for them to actually see this. So, for example, if you see this different flow regimes, and in that you had co-flow, counter-flow condition, and T-shaped channel, co-flow, microfluidic channel system, and this various different flow systems are there, and they are I will be showing you some of the videos that will be giving you some idea about the microfluidics flow systems and how the different designs are being generated. So this designs which I wanted to tell you is, first one is this one. If you see, this is the situation of co-flow. So I will be showing you a video. Yes, this one, if you see here, you see this particular scenario is the situation of the flow. One dispersed phase is coming, and from two side continuous phase is coming up, and they are creating stress for the dispersed phase, and drops are being formed. So in the similar situation, jetting can also happen, but for now only the drop formation and the drop conditions we will be discussing, and like how wide fractions will be calculated in this. So different types of flow regimes will be formed, and different uh, dripping and jetting, uh, and this I will be showing you, just wait uh, now. Yeah, okay, so this is done. Now this, the first question is this one: in wide fraction calculation, is just knowing the flow rate of two flow rages is sufficient. So can you only know the calculate the volume void fraction if you are just knowing the flow rates of two phase? Options are: if flow rates at which two phases move is constant, there is no sleep between two phases. Taylor bubble moves with the average velocity higher than that or lower than that. So which of the following is correct? So if you remember the discussion that we had in the second lecture, I think. So there, in the first lecture of the week, you have been taught about wire fraction calculation, and various correlations you have been taught, and here you came to know that this different factors like density difference ratios, viscosity ratio, diameter of the channel, and the surface tension is the one that plays the role in deciding the wide fraction. And this wide fraction calculation involves considerations at various levels. So, if you remember various correlations that have been told is sort of self-explanatory and experimentally calculated, but the thing is, like, if the flow rates at which two phases move is constant, there is no sleep between two phases, the Taylor bubble moves with the height. So yes, this one is right. That Taylor bubble moves with the higher average velocity. Whatever the average velocity will be, that is mu TP. So UTB U bubble is more than the UTP, which is the average velocity. Average velocity. And if there is no sleep between two phases, if flow rate at which the system system is moving, so this involves the and again you have been told that this image analysis could also be used in order to calculate the uh, the word fraction. So this one in this we see this, if the flow rates at which the two phases move is constant, then this q that generally doesn't happen, but if it is there, then that can be used as a parameter in order to calculate void fraction if there will be no slip, and this, so ABC is the correct answer, is correct answer. And now the next question, which is here, this says most frequently used method for void fraction calculation is. So this could be multiple choice question. So if you see, like, image analysis, solenoid valve, neutron radiography, image processing, electrical resistance method, electrical capacitance method. So which of the following is used for the calculation of the void fraction in the channel system and in the two-phase system? So if you remember, yes, you remember this here, you have been told that the biofactor measurement in the channel is often difficult, but the most important measurement based on the image analysis. In that, you have been told that the solenoid valve method, which have been borrowed from the Bao et al., and then neutron radiography, image processing, electrical resistance measurement, and the electrical capacitance measurement. So these all are there, and these are a method. So for this particular problem, if you see the options, option A, B, C, D, E, and F, all are correct. Okay, so this is the method for word fraction calculation. So can correlation developed for large diameter channel may be used for the small diameter channel to calculate word fraction? Directly, they cannot be, but if you change these correlations a bit in some limit, some modifications will be required for these already well established correlation of the you know this channel, well established correlation of the channel. Some modification is needed, and after that modification we can use them, because if you are going for the small diameter channel, then the surface effects will be dominating, and uh, under those limit, various factors will be coming up in terms of Weber number and the capillary number, leading to the comparison of the inertial and the viscous forces with that of the surface forces, and then those factors will be leading up, that hasn't been taken into account if we have calculated the things for the larger diameter channel. So that's why this discussion came up into the picture, like the various correlations that is there, like Armand type correlation. It is there. Yes, this is the one that has been discussed, and in that Armand type correlation, the homogeneous model, uh, Chisholm correlation, and then this spreading and chain correlation, all were there. And this is also, so all are correct. So these were multiple choice question, and if you see this, uh, this is the one. So which of the following is correct about the various correlation of void fraction? So Armand type correlation and the homogeneous model depends on the ratio of the density of the gas to that phase. So if you want me to show in the slides, so this particular slide explains that, like, see various Armand type correlation had these different sub correlations, and then we are having this Butterworth type correlation. So Butterworth type correlation, you see, that involved some other factors which have been taken into account, like ratio of the density and the viscosity along with the quality. So that is coming up into the picture, and then this this CISC group correlation again took the consideration of the surface tension as well as the channel diameter into. So this as you are progressing, you are looking at different correlations, coming up more realistic picture of the scene, and that's what the necessity, so that we will be close to the experimental thing. So this particular uh, uh, explanation for this, like which one of the following is correct about the various correlation of the void fraction, the option is Armand type correlation and the homogeneous model depend on ratio of the ratio of density of the gas to the liquid. Okay, so let's see whether it is correct or not. So this only homogeneous model and the Armand type correlation both were having the C value constant. So you had Armand type correlation in the Armand type correlation, Armand type correlation. In that you had this alpha equals to C beta. So it is the word fraction. So this C equals to 1, C equals to 1 for homogeneous. Okay, and this C was something 0.833 or 1 divided by 1.2. This was for Armand correlation. And then there were two more where C was the function of beta and the rho g to rho L density ratio. And also for this was true for two things. One was Chelson, Chelson, Chesel correlation. Wait, correct it. Yes, Chesel correlation. And another one was correct for speeding and chain correlation. So, so you see this density ratio is coming up into the picture for these two. So our Harman type correlation and the homogeneous model all depends on. No, this is not correct. Harman type correlation homogeneous depends on ratio of viscosity. It is also depends on both ratio of the gas to liquid and the this. No, this is not correct. Only the last one is correct because those are constant. Chisholm correlation and splitting correlation depends on what? On depends on the ratio of the density of the gas to the liquid phase. You see, so B option is correct. CISC correlation is suitable for what? Before that, you see this sixth question. GV model depends on viscosity. So what is the GV model? If you remember this GV model, so I will be telling you this GV model. You see, this was under Butterworth type correlation, and this GV model had different parametric value that will be in the expression for the word fraction. That was this alpha thing. So this alpha equals to 1 upon 1 plus a 1 minus x by x to the power p rho g by rho l to the power q and mu l divided by mu g to the power r. And these value for were different for different PQR A, and A values were different for different models. And in that JV model was there, and yes, JV model for the JV model R equals to 0. So for this R equals to 0, so it is independent of the viscosity, so it depends on the viscosity. This is false, so this one is false. So now you look at the seventh question and see if you could get some insight about the same. Like CISC correlation is suitable for channel size. So the option is it is suitable for the channel which is less than 0.5 mm, which is more than 4 mm. It is suitable if the channel size is between 0.74 to 3.74 mm, and none of the above. So which of the following is correct? So we look at this, and I will be giving you 1 minute to solve this. Uh, and I hope you are getting some insight. And this some bandwidth problem is there, some lag. Yes, and these particular lectures will be recorded, and these will be in the same uh, queue at the SWAYAM portal, so you can also visit it, and will be helpful in solving the weekly assignments. And these all questions are entirely based on the content which has been taught in the particular week for week which the lecture is being delivered. For example, this is for the week 4 content, and let's solve this. CISE correlation is suitable for channel, so you solve it. So we will be looking at various different regimes, and then various small definitions like sleep ratio, hydraulic diameter, and Martinelli correlations, and everything we will be having bit by bit, so that all the content and the slides that was there that has been taught to relate you and to give you some glance of two-phase flow, and in that is specifically the void fraction and the liquid flow regimes that will be clear to you. So this, I hope you have solved this, and this particular uh, question will be involving the understanding of CIRC model. And if you have, if you remember, the various points that has been pointed out while discussing about the CISC model is the one, this one, where you have been told that this this is this a number of the other correlations have been proposed for the microchannels. In a small diameter channel, the void fraction has been observed to dependent on the channel diameter. So yes, the channel diameter has been considered by the CISC correlation. And then you see here the CISC correlation is suitable for 0.74 to 3.74 mm size channel, and above or below which it is having less uh, correctness. So that's what was the question all about. So the answer to this question will be the option number C. So C is correct. So define hydraulic diameter. So if you see, so hydraulic diameter is the one that you need to define, and these are some more questions. And meanwhile, we will be discussing some more questions. We will be having some points in hand, and some instability thing we will be discussing in detail. So, so this hydraulic diameter is the question that is in hand, and this hydraulic diameter is basically the the diameter which is being calculated based on the area to perimeter ratio. So this is a bit generalized one, and it actually averages over the same. So if I tell you this hydraulic diameter DH equals to what? 4 times area of area of cross section or whatever, say you are going to calculate the DH to the perimeter meter. So we will be solving some questions over this in upcoming questions. So now what is Martinel correlation? So just explain about this. What is Martinel correlation? And this Martinel correlation, if you remember, there you had this was more general in various terms, and then there you had this well matched with the experimental results, and Martinelli correlations. So this Martinelli correlation is the factor that comes up into the picture, and this Martinelli correlation is a model system uh, for this two-phase flow void fraction calculation, and this uh, mostly whatever experimentally you are getting. So through the experiments, you are getting some results, and then this void fraction calculation based on the the parameters and the forces like viscosity ratio, surface tension, and the diameter of the channel, basically the dimension of the channel if it is not circular one. Then this this requires some sort of understanding of the factors which are there, and which actually ease down the thing. So This two-phase flow model is taking those parameters into account in order to get some insight. So this Martinelli correlation, or sometimes we call it like Lockhart-Martinelli correlation. So this this is question number 10 solution we will be writing. So I will write here your question number 10 solution. So this Martinelli correlation is the ratio of pressure drop for the liquid only flow to pressure drop for the gas only flow. So pressure drop for the liquid only flow to pressure drop for the gas only flow. So I will be writing it as if x square equals to delta P for the liquid only flow divided by delta P for the gas only flow. So that's what for the Martinelli flow. So sum of the acceleration, pressure drop, frictional pressure drop. So question number 11. Question number 11. So sum of the acceleration pressure drop plus frictional pressure drop plus the another one that is given is the hydrostatic pressure drop is the total pressure drop. P hydrostatic is the total pressure drop. Whether this statement is correct or not. So this statement is correct first of all, and then this pressure drop calculation, if you remember, uh, there you had the coming up of various terms that will be anyway considering different pressures, and that was getting leading to the various flow morphologies coming up into the picture. So this is true. This is true. This is P delta P of total. So the friction need to be considered. That will be actually coming up with the fanning factor. It's thing there you had two fanning factor and there 4FL V square upon 2ZD. That will be giving you the pressure drop. And now let's begin with the next problem. And this actually happens at the steady state. So the question is sum of the acceleration pressure drop, frictional pressure drop, and the hydrostatic pressure drop is the total pressure drop at steady state. So the answer is steady state. Okay. So what is Rayleigh plateau instability and how did it lead to the breakup of jet? Explain. So you think about this question. Meanwhile, uh, I will be telling you. So the Rayleigh plateau instability comes up into the picture in the jetting also when the jet is changing itself into the drops. So first jetting happens if the flow rate is high, and then that jet sprinkles into the droplets gradually because of the undulations caused at the interface. Both sides, actually both sides. So So we will be using a YouTube video, and we will be citing them uh, for the contribution. And so this particular video will be dictating about the Rayleigh plateau. So this video is from Cosmic Noon, and this will be as a reference for us. And if you see here, then what actually happens is, let us delve deeper into this. Maybe no, let me just open this in other way around. Wait. Let me just open this other way around. Yes. So let's open this in this way. Yes. So here you see, if you look at this, yes. See, these these are the tap water. From a tap, uh, water is falling down, and you see first the jet is coming, and that the jet drips down. So in the high speed, you see how this braking is happening, and you see in this one small droplet levitates between. See how the brake is happening. This is at 1000 fps. So now you see what are the forces that is leading to the braking, and what are the forces that leads to the subsequent uh, subsequent rock formation. And if you see this, this actually happens because let me explain this. This actually happens. Where is the which question was this? Yeah, question number 12. So question number 12. So here you see this is the stream of the jet. It is falling from the tap, suppose, and this jet is undulated because of the external force. And finally, this undulation grows and leads to the drop formation in this sense. So here, if you see this arc, this particular arc, which is here, this particular arc, this is the one radii. This is the one radii, which is for the inside stream, and there will be another radii of the curvature, which is this one for the outside. Then this is inside. So there is another R, R1 R2. And this radius of the liquid column will be no longer constant. The radius of the liquid column will no longer be constant. Why they will not be constant? Because there will be Laplace pressure difference. Because of Laplace pressure difference, that is delta P equals to gamma times curvature, and that is equals to surface tension time 1 apart first principal radii plus 1 apart second principal radii. So this curvature difference leads to the delta P, which will be leading to the excess pressure and subsequently drop formation. So this is nothing but the Rayleigh plateau instability. So this Rayleigh plateau instability, if you see here, if I actually draw it correctly, this is like this, which is like this, and this one is low pressure region. Low pressure region. Okay, this is low pressure region. Another one is the one is the high pressure region. High pressure region, and this is the water column. This complete is the water column, which is coming from the tap. Water column. So this is water column coming from the tap, and if you see this from the high pressure region, pinch point happens. So the drop detaches from the high pressure region. So here pinch point is there, and this pinch point leads to the subsequent droplet formation. So actually what happens, this actually happens at the high Reynolds number thing. So as the flow is high, it happens usually at high flow rate. So you can actually neglect the effect of viscosity and the gravitational thing from the side, but in the vertical direction that is there. So the water stream has already broken down because of that into small little droplets and in horizontal motion, and it will not be affected by the gravity. So in the cases just consider, the cause of the instability is statical and the phenomena is independent of the general translational motion of the jet. So this actually happens. So that is all for this particular instability, which was the Rayleigh plateau instability. And now we will be heading towards the next question, which is what is Kelvin-Helmholtz instability and how does it lead to the vigorous undulation and the shear? Explain the mechanism. So I will be coming up to this. You just think about this. So so that you actually understand the question well. And yes, so this, yes, yes, steady state, yes. So the Kelvin-Helmholtz instability is actually happens when there is the flow rate difference, and actually this, if you remember, the if there will be flow rate gradient among the two layers, and this is actually there whenever the two fluid are flowing uh, over the one another. So this Kelvin-Helmholtz instability, which is the 13th question, is the Kelvin-Helmholtz instability. And this Kelvin-Helmholtz instability, if you see this uh, Kelvin holds instability. This actually happens when there is the two layer, one is surpassing the other. So there is the velocity. And if you remember how this happens, if this is the situation at some junction, flow is happening here and one. So if this flow was happening this direction only, but the velocity is un u, and suppose un is more than u2. So in that term, there related to the un, there will be flow in this direction. Okay. So what is actually happening here? The faster flow is happening, and here also the faster flow is happening because the region is squeezed, and because of that, the other regions are the region for the slowers. This is the slower, this is the slower, and this is the slower. So because of that, slower and faster region build up, there will be more velocity here, less velocity here, and here there will be more velocity, the less velocity here, more velocity here. There will be undulations coming up, and these undulations leads to the pressure difference. So because of that, this will be of low velocity, this will be of high velocity, this will be of low velocity, this will be of high velocity. So here low pressure zone, here high pressure zone. So here high pressure zone will be there, and because of which there will be a force acting in upward direction, downward direction, and the upward direction. And this force will lead to the undulation, and subsequently this will lead to the breaking of the, the thing. So if you actually look at the experiment that is there, so if you want to look at the experiment that is there, I will be putting this video also in the reference section. So this is by 60 symbol Kelvin Helmholtz instability, and this is this one. If you see, you will actually appreciate how the things are happening. Here you see how this happens actually. If you see, initially it was actually there was no undulations, and see, yeah, this happened, and then this Kelvin Helmholtz instability growth. So this also happens in the cloudy region. So that's what for this particular instability, and I hope you learned this, and I have demonstrated it through the video also. So this was all for the Kelvin Helmholtz instability, and now if you see, we are done with the question number 13. So what is Rich-Mayer-Maskov instability? So what is Rich-Mayer-Maskov instability? This is the question that we will be looking at now. What is Rich-Mayer-Maskov instability? So this Rich-Mayer-Maskov instability basically comes up when there is the density gradient, or density difference, and this, if you see this one, this actually there are few points about this instability. The point number one is, like Reshmer-Maskov instability occurs when two fluids of different density are impulsively accelerated. It occurs when two fluid of different density is impulsively accelerated. Okay, so when this happens, then normally this happens by the shock waves. So let me connect it. Yes, yes, yeah. Normally this happens by shock wave. Okay, and the next is like this instability begins with the small undulation. So the development of the instability. So stability starts with small undulation, small undulation, or say small amplitude perturbation, perturbation, which initially grow linearly with time, which initially grow linearly with time. Yes. So that's the one thing. And now afterwards, what happens in this particular instability, which is Mascom instability? After this, there will be formation of droplets because of the nonlinear regimes coming up into the picture. So next to this, next to this, nonlinear regimes with bubble appearing in the case of light fluid penetrating a heavy fluid. Next to this, nonlinear regime coming up into picture as light density fluid, penetrates heavy fluids, heavy fluid, and the spike appears in the case of heavy fluid penetrating the light fluid. So bubble appear when the light fluid penetrates the heavy fluid. Picture as light fluid bubble appears, and the spike appears if heavy fluid penetrates light fluid. Okay. So what happens? A chaotic regime eventually is reached, and the two fluid mix. This instability can be considered the impulsive acceleration limit of the Rayleigh-Taylor instability. So there is some relation between the Rayleigh-Taylor and this. So if the in the Rayleigh-Taylor the this impulsive acceleration limit is there, then this happens. So what is the Rayleigh-Taylor instability? If this term came up, then you should know this. So so the Rayleigh-Taylor instability. So let's include this also in your discussion, which is the Rayleigh-Taylor instability, which is Rayleigh-Taylor instability, ability. And if you see this particular instability, so this is a type of hydrodynamic instability caused when this is a type of hydrodynamic dynamic instability ability caused when caused when instability caused when a fluid medium a fluid medium with high density is set over over fluid medium with low density. Okay. A ripple gets set up, causing turbulent flow pattern. So, ripple gets set up, causing turbulent flow pattern. Flow pattern. Okay. If you see this one, this actually happens like this. The flow setup is this is the interface, and this is the high density fluid, density, low high, and this is the lower density, and these are the row edge, row edge, row edge. Okay, so if if you want me to go a bit deeper into this, for example, the dispersion correlation, in terms of dispersion correlation, that is the another thing in order to understand the extent of the instability. So that is not needed here. So if you see the direct Taylor instability reality, that is actually caused because of the density difference, and this actually happens if you have that contrast in the density of the two media. So that happens when you put coffee. Coffee ring effect is also somewhere connected with this. So here, if you see, if I explained it a bit more, this is the interface, suppose. So if this is the second medium, this is the first, means rho 2 is greater than rho 1 if you are considering. Then, and the gravity should act downward. Then what actually happens? Because of this, there will be this interface go up, this interface come down because of the Bion forces which is acting, and gradually what happens? This will grow. The grown one will be like this will be like this, and this will be coming up like this, but still it will be growing. And gradually what will happen? There will be these mushroom formation like this one. These mushrooms will be coming up into the picture. So 2 1 like that, and gradually these mushrooms will grow up, and the phenomena will happen. So I will be demonstrating you this with, yes. So this will be a clear cut idea. So I will be citing this video also. Uh, this video is by uh, 5 fluid dynamics, which is about Rayleigh-Taylor instability. So I will be putting it in the reference. Yes, this one. And what actually happens is very interesting. You see. So, so what actually happens is this one, like like uh, when see these are the two bottles. This is the fluid one, fluid two. The density is 1360. Its density is 1000. This is corn syrup and this is something else. And see how these differences there in the viscosity also. So once you put it one after that using the sleeve, and you just remove the sleeve so that they just interfaces just come into the contact. Yes, see this how this happens. So this is the Rayleigh-Taylor instability, and that's the main agenda of getting visualization of the phenomena that just happened. So I think this is clear to you, and the this instability is happening yeah, because of the density gradient among the fluid, and that's what the main picture is. So now we will be going to the next problem, and let me see if everyone is with me. Yes, so we are in the presentation mode. Yeah. Now, Rich-Mears-Mascov instability we have discussed. We have discussed, along with that, we have discussed the Rayleigh-Taylor instability. Uh, okay. And so we have discussed both. And now we will be going, what are the different flow devices in the microfluidic setup? So, what are the different flow devices in the microfluidic setup? Just you copy this question. What are the different flow devices in the microfluidic setup? So this is the next question in our hand, and if you remember, this was there in the discussion in the class. This was a part of the liquid regimes, flow regimes, and in that especially you had different types of channels that was there, like I mean this uh, this T-shaped channel. In that T-shaped channel also there was like how you are putting the continuous and the dispersed phase, and the angle at which the channel inlets and outlets are arranged. So now let us just look at the various different flow devices that are there, and see. So in the lecture you have been explained about this, so I will be just taking the help of this tool so that we actually look at this. Yes, yeah, this came up here, and now yes, so you look at this. So different flow regimes that was there is the one in hand. Like flow regime in the liquid flow depends on the structure of the channel. So like you had different type of channel, which was T junction channel, flow focusing channel, and con flowing channel. So in the T junction itself, you had a different possibility, like the channel is arranged in this way, or in this way. So this channel, if you see, uh, for the flow focusing one, the shape is like this. The flow focusing one you are having, uh, suppose this is the outer boundary, and the one dispersed medium is coming from here. Okay, and this is the stopper. So this is the stopper here, and one fluid is coming up and another one is coming up. So if your one fluid comes up here, it seems like it is cutting the medium. So here there will be squeezing and the subsequent drop formation. So like the video I have. So this actually happens in the flow focusing channel system, and another one is like conflowing channel. So in the conflowing channel, there will be no stopper. This will be like continuously conflowing channel. So in the annular region, the outer flow is happening, and the inner core region, the inner flow will be happening. Flow of both the phases is parallel to each other in the conflowing region, and in the flow focusing region, the continuous phase flows in a perpendicular to the dispersed phase when phase come in contact. So that's the point and the answer to the question. And there are three modes of operation in the T junction. So about that also there is a question. What are different modes of operation in the T junction? So we will be looking at that also. So let me see where is that question, which was where we have solved. What are the different flow devices? Okay, and this question like 16 is the dripping flow regime is observed at the low flow rate. So if you remember, jetting happens at the high flow rate, dripping regime observed at the low flow rate. Yes, it is observed at the low flow rate, so the answer is true. Which are the different modes in the liquid flow operation in the T junction in detail? So we will be going to detail it. So let me just take the question to the point where we will be explaining it. And if you see, we are on the way to explain various things, and similar questions will be in the weekly assignments somewhere, somewhat modifications of the same concept that has been taught. And this, you see, there are different flow things. First is the that can happen the T junction is the cross flowing. Second, what can happen is the perpendicular flowing. And the next what could happen here is the cross flowing, perpendicular flowing, and the head on flowing. Head on flow. So head on flow, cross flowing, perpendicular flowing. So this is the situation for the cross flow. So similar type of channels will be there in the cross flow and in the perpendicular flow, but the channel dimension will be a bit different for the head on flow. So if you see this, let me take different color. Yes. So this is the continuous medium. This is the dispersed medium. And the flow is happening in this style. Okay. And here the perpendicular one, this is the dispersed medium, this is the continuous medium, and the flow is happening like this. And this is the continuous, this is the dispersed, or any dimension, it doesn't matter. And this happens like this. So this is the head on. Okay, so that's the three thing. So in the cross flow, continuous phase is straight channel, droplet shears off by the cross flowing stream, and in the perpendicular flow, dispersed phase through the straight channel, passes through the straight channel, and so to be narrow droplet size distribution. Here narrow droplet size will be forming. So narrow droplets will be forming here. Okay, so this question is completed now. Now I request you to solve the next question, which is again we have few more questions. Question 24 questions we are having, and then afterwards we will see what to do next. So we have solved till 17. Till 17 we are done with. This we have done. All the questions we have done. Now you see different flow structures of the flow device is decided by various factors that are they explain in detail. Then explain what are they, and then we have to explain them in detail. So this question is okay, good to discuss, and you may be clearly knowing the things. So let me see if someone is there. Yes, yes, this is the one. And you just think about this question. Meanwhile, I will be coming, and we will be going to discuss this in detail. Okay, so the question is different flow structure of flow device is decided by various factors. What are they? Explain in detail. So what are that various factors? And if you remember, uh, you just think about this, and we will be discussing about the same. Yes, so I hope you have gone through the question and you have solved it. Now we will be discussing the solution for the same. And if you see this, uh, okay, so if you see this, different flow structures of the flow, the regime is decided by various factors. What are they? Explain in detail. So the one that is the contact pattern of the fluid at the inlet is the one thing that decides. So the and this how the fluid is contacting is the one thing that is that decides the structure, and then the wetting property of the two fluids means surface tension wetting property is of two fluids. If it is a multiple system, then all the fluids. And the third is the interfacial tensor, force of cohesion or adhesion. Here we have to write force of cohesion or adhesion. Yes, force of cohesion or adhesion. Yes, and then this force of cohesion or adhesion, force adhesion, wetting property of the two fluid. Yes, and the interfacial tensor between the both interfacial tensor between fluids are the major factors which decides the apart from this the density rheological property logical properties like density ratio viscosity ratio and then different elasticity or moduli if it is there, then they also play a role in deciding the flow structure for the phase in the microfluidic cell. So that's then. So calculate the hydrodynamic diameter for the okay. So let me just take this question to the place. Let's take both the questions because we have to solve both of them. So let's see. So this is the question number 19, and then we will solve question number 20. Just give some space over here. Yes. So here, let's take the formula for the hydrodynamic diameter that we have just written here. That will be of help. You see this, and the question is direct. So the area, suppose the the this is the circular, and then another one is like circular one. Now, okay. So let's solve first the square one. Then we will solve the circular one. Okay. So let's take this to up. Yes. So this is square duct. Suppose the side of the square duct is A. Okay, so the duct size is A, and as the duct size is A, the area will be A square, and the perimeter will be 4A. So if you see, if you use the formula which says 4 area will be A square and the perimeter will be 4A, then this comes out to be A, which is 1. And here you see the square channel side is this. Okay, and for the another problem which is here, the circle of radius 1 micron in diameter is 2 micron. Okay, now or the radius is 1 micron. So this will be clear to you, like radius or diameter in terms of whatever you solve. Then this will be 4 into area is 4. No, area is pi r square. Pi r square. Okay, and the perimeter is 2 pi r. So this pi cancel, and this comes out to be 2 r cancel. So this comes out to be 2 r, which is 2 micrometers. So now you see this particular question had the clarity about the hydrodynamic diameter, and that will be anyway used. So the two thing that is here is the one which is the hydrodynamic diameter that we have just calculated, and the how this hydrodynamic diameter will be used in order to get the flow the information about the flow structure and its quantification in the channel. So the this we have solved, and now let's discuss about this. So this diameter one will be the same, and the question that we have already solved here, this was there. Where is this? So let me just take that question at the study. Yeah, this one. No? Okay, this one. This question, if you just want to be a bit detailed, so this the answer to this problem was the at steady state. Okay, there is no issue. So this the expression, if you write, this was like dp by dz total equals to minus dp by dz acceleration plus everything will be negative, so drops will be calculated with that of hydrodynamic acceleration and dp by dz friction. So so this term is often important when there will be two-phase flow with phase change. Important when two-phase flow happens with phase change. Okay, that is the one thing. And then this along a pipe system, the term may appear, which is abrupt change in the flow area or the flow path. Pressure drop is controlled and regulated device through the valve or orifice and the vents, and that may also lead to the extra frictional thing. So this happens at the steady state. So this entire expression is at steady state. Okay, so that is the one problem And another question that I want to pose is how fanning friction factor and Darcy friction factor is related. The options are: A is F fanning equals to 4 times F Darcy. B is F Darcy equals to 4 times F fanning. C is fanning equals to 0.4 times F Darcy. None of them. So if you remember the discussion, I want you to solve this first. So the answer to this problem is the option number B, which is F Darcy equals to 4 times F fan. Which of the following is true? For this we have solved. And now moving to the next problem that was there. There are some problems still remaining. Yes. So we have solved this 19. 18 we have solved already. We have solved 19. And here all the questions we have already solved. This also we have solved. These all we have solved. So this 20 also we have solved. Now the question number 21 we are going to solve. So you just look at the question. CISE group correlation considers the effect of which of the following factor? Which is the density? First is the density ratio, then the viscosity ratio, only viscosity of the liquid, surface tension, and the channel diameter. And if you remember the discussion while we were going through the CISE correlation, and I will be putting the slide of the CISE correlation so that we actually relate to the content that CISE correlation has given now. So where there you have been told that this CISE correlation, if you remember, the we will be actually having this one. Yes. So let me just put it here. Yes. If you remember this one, here you see the effect of density ratio is there, effect of surface tension is also there, and then the channel diameter is also there. These all three are correct. The liquid viscosity is taken into Newton, not this one. So ACDE is correct. So ACDE is correct. And also the next problem, which says the in CISE correlation, the X equals to this, which is the quality, and the quality is defined as mass of the gas to mass of the gas plus mass of the liquid equals to X. Okay, so this you see, this is the function of gas liquid density and the word fraction beta. So this is true. So define the quality. We have already defined the quality. This is for the gas liquid mixture. And now different factors contribute to the overall pressure drop in Taylor flow regime is pressure drop in the continuous phase sludge and the pressure drop in the cylindrical region of the bubble and the drop. Pressure drop, interfacial pressure drop at the front and the rear end of the bubble. None of the above. And if you closely look at this, all ABC is the correct. ABC is correct. Okay, so all the three options are correct. So now we have done with many problems, and I will be now providing you some of the problems that will be actually involving the conceptual understanding of the flow at the T junction, and some questions around some numerical kind of question we will be solving. But before that, like some problem we will be discussing about the flow focusing device. So which of the following is true for flow focusing device? Okay, so let's look at that. So question says which of the following is true for flow focusing device. Okay, so if you see what is the which of the following is true for flow focusing device, here you see this is already explained, and you see this says like the flow focusing device is the one that I have already explained you. Is we have drawn it somewhere. Let me take that. Yes, this is the flow focusing device that I am talking about. About this flow focusing device, which of the following is true? The options are option A says disperse phase at the flows through the side channel. Disperse phase flows through the side channel. Disperse phase flows through the constriction channel. Okay. Then usually generate droplet uh, usually generate droplet rather than plug. Plug and channel wall contact can be avoided. Okay, so now this is here, and if you see this, what are the correct options? So this this and This is the correct one. Continuous is at the side length. So this should be continuous. So this is wrong. This should be continuous. Okay. So about the flow focusing channel we have discussed, and then this in the regarding dripping and jetting design, which will have highly spherical droplet, which will give highly spherical droplet. Okay, so which will give highly spherical droplet. The options are dripping, jetting, dripping at high flow rate, jetting at low flow rate. Okay, so which of the following is correct? Just think of this and look at the problem. Uh, So the answer to this problem is the dripping design. So dripping design actually gives uh, good spherical droplet, and it happens at the low flow rate. So this is incorrect. This is incorrect. This is also incorrect. This is correct. Here high flow rate is given. So now another question I want you to tell me is this one. For which of the following? For which of the following? For which of the following fanning factor is more? Fanning friction factor is more for 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 fanning friction factor is more for channel diameter 1 mm or 100 mm. If if velocity of the the uh, water is 0.16 meter per second. For what it is more? So the question is true, is false. So it says that for 1 mm you are having more fanning fraction than the 100 mm, giving same as it is water, then you are having density to be 1000 and the viscosity to be 0.01 pascal second. So uh, 0.001 pascal second. So now the fanning friction factor has been asked, and the answer to this is what? So you solve this, and As you remember the definition of the fanning friction factor, there is the clue. Definition of the fanning friction factor, there you have been told about this. And this fanning friction factor uh, related to the Pauchy's equation and Darcy-Weisbach equation, and there you came to know about the same. So if you actually see how this is coming up into the picture, you will come to know. But the thing is, like, the capillary number and the Weber number is also at the play, because you are playing things at the very low constricted microchannel. And then this if you remember, this is what? This is delta P equals to 4FLV square upon 2GD. Yes, and velocity is given, and you see delta P is here. You can divide it by rho g in order to get some insight. But from here you see the the factor is there, and at the same time the whereas other things are there. So this is true, as you will, when you will calculate the same, you will get uh, value 0.1 for this the factor this for this you will get the value of fanning factor to be f equals to 0.1, and for this one you will get the value to be 0.007. And from here you know this what is correct. So f is more for lower diameter channel, so it is true. So that is the one thing. And now if you want me to give you one question that I want you to solve, similar question you will be getting here and there in your assignment. The question is like, in a tube very thin tube of diameter diameter 0.2 mm, the density is mass flux is 1001 kg per meter square second. Obtain the two-phase pressure drop and obtain the two-phase pressure drop considering gas mass flow rate to be 30% of the liquid the, the flow total flow rate happening in the channel or in the thin capillary, the viscosity you are given with very low viscosity for the gas, and for the liquid you are given with 0.001 kg per second respectively, and the corresponding density of the gas is 2.4 kg per meter cube, and the density for the liquid is 100 kg per meter. So solving, the options are A 56.25 into 10 to the power 5, B 56.75 into 10 to the power 5, C 50.30 into 10 to the power 5, and D is 46.21 into 10 to the power 5. So you solve it, and the concepts will be the calculation that we had for the Taylor flow thing, where this consideration of the upstream and the downstream head, along with the pressure drop across the sludge and the plug, has been considered in the picture. The 56.3530 will be the answer to this, and then that's similar problem you have been explained in the class, and this this actually tells you so about the calculation for if both the phases are present over there. So here, like both the phases were present, I mean this uh, the phase like gas and the liquid, and corresponding values for all the phases have been given to you. So this is the overall criteria, and now the next question that I will be telling you is this one. So the answer to this will be this one. And now next question is, so we are having very less time, and this actually briefly these two lectures were about the flow regimes, and then the flow conditions. So if you see, if you want me to show you some of the videos of the uh, T channel that is there, and if you look at them, you will come to know that this, suppose this one, if you see, let us see if it comes up. Yes, it is coming. So this is the one which is happening in the T junction. So water is coming from top and silicon oil is at the bottom, and you see how this drop is coming up. So this is liquid system, and dripping kind of thing is happening. Drop is forming, and there the neck formation is happening, like we have discussed. This is the first situation of the modes in which T junction can operate. You see, this has been taken in 2000 FPS, so 2000 frames are getting clicked in 1 second. And this, you see, uh, if you want me to show you next one, which is again somewhat different version of this. So the sludge means this was the droplet thing. If it's kind of sludge coming up, then the water flow rate is increased. You see, it's kind of capsule, and these are kind of Taylor bubble kind of thing, a Taylor drop kind of thing. You see, they are not touching. This particular region is anyway vacant, so it is not touching somewhere. So these are like there is still the small thin oil region. And if you look at this, later this size grows as you increase this, and later we have somewhere, I mean somewhere, there is a formation of segregated region, maybe this one, or yeah, this is C. This is the annular flow region formed up. You see, this is continuous annular region. So this may break if we if you actually see how this breaks up. The beauty which is there, yes. And here you see, because of some defect or some droplets came up. So that's the one thing. And now the question that I am asking is, which of the following is true for? Which of the following is true for Friedel correlation? Okay, so the options are, this is for horizontal flow, this is for upward flow. Okay, then this is used for, most widely used for, small channel. This considers the effect of density ratio. Consider the effect of considers the effect of considers the effect of density ratio of two phases, then viscosity ratio of two phases, and it also considers the effect of what we call surface tension or interfacial tension. And the, these are multiple choice questions, so you have to be very clear about the option that you are putting in. Volume fraction, that is easy or beta. So let me put it in the frame. Yes, yes, now it is visible as well as I think. Yes, yes. So you think about this, and we will be looking at the same. I will be joining. Just you think about this in 1 minute. You put all the options down. What you think is correct. This is the multiple choice question, so many options can be correct. Okay. So, as far as the discussion is going on, this is all about the fourth week, two lectures. The one was for the word fraction calculation and with various correlations coming up into the picture, and another one was liquid flow regimes. So, so almost 30 to 35 questions we have solved. They're still on the way. Still, we are having 5 to 6 minutes, so we will be solving one or two more questions. And the thing is, these questions will be anyway helpful in your final certification examination, and at the same time, in solving the assignment questions. So, assignment questions will be single choice questions, so there will be not that much trouble. But in order to make you thorough with the content that has been taught, the options deliberately we have put in to be the multiple choice questions so that you actually had thought over each option rather just picking up the right one. And when you see this, this is true for horizontal and the vertical channel. So you need to look at the slide where it has been taught, and this widely used for the large channel, not for the small channel. So this should be large one, and this actually considers all these three effects. So option A, B, D, E, F, G is correct options. Okay, so these all options were correct. Well, and and let's think learn about the various dimensionless number so that it just remind you what they were. Faraday number. So Faraday number is what? Anyone? So the Faraday number is the ratio of inertia to the gravity. To the gravity. And this actually comes out to be u square by gt. And the Weber number, if I ask you Weber number, it is the ratio of the inertia to the surface force. And this comes out to be rho utp square diameter divided by. So, so that's the main thing. And this actually tells us how much important the analysis is for the ratio. With this analysis are various numbers in terms of relating the extent of other forces like surface gravity and the inertia, and sometimes the viscous. Uh, that comes up with the capillary term, and the capillary number actually takes care of the thing, and that is true in some sense, because as the channel dimension is reduced, the factors that are coming up into the picture is actually increased. But the thing is, if you see the thing, like the discussions that we had here, if you see this video, it says that like lots of air bubbles are floating in the continuous channel, and now the Taylor bubble is coming up, and you see the various phenomena is happening. So the calculation of the total pressure drop that we had has been calculated for the Taylor bubble condition only. But there are more different natural general scenarios for which still the gaps are, and the current researchers should be there to correlate uh, the existing uh, experimental uh, phenomena with the correlation, or some new correlation that you can come up with by modifying some of the existing and considering the various effects that are yet to be considered in order to have the full control of the model and the experiments that are happening. So you see how smoothly this is happening. So I actually acknowledge these two videos. These are here. It was there. So same is for there also flow design and well for, and this I have was before, and flow design is increasing and if you see this with a different kind of interest. So these two, just I wanted to give them credit. So where are they? Let me see. Yes, yes. So these this was the another video, but where is this one? So this was week 2 or week 1 that I actually. Oh, where is that? First one is not that. So those videos are there, and I was to acknowledge them along with the other, and that actually eases up the discussion and puts up some more clarity. Okay, so that's what for today's lecture. We have discussed around 35 questions related to the week 4 content, and I hope you learned something, and this will help you in solving the assignments, and at the same time it will help you in some sense in the final examination of the course. So thank you so much, and we'll meet you in the next class. So thank you.